This is lecture 14 on the topic of cosets. It's part of a pure mathematics course in finite group theory at junior and senior, although now senior level. The first author is Barnard here, and here's the text that I'm using for this course. It's in the Teach Yourself series, and the title is Mathematical Groups. Right? Today's lecture is one of the major themes of this whole course. It's one of the major chapters, with one chapter per lecture, or one lecture per chapter. The lectures come in parts, or sessions as I tend to call them. And the main result is that it's Lagrange's theorem, famous result in finite group theory, and you know already that Lagrange's theorem simply says that the order of a subgroup, the size of a subgroup, is a factor. It divides the order of its parent group. So, for example, say you had a group of size 12, has 12 members. Its order of the group is 12. So that means it's possible subgroups could have a size, an order of 1, 2, 3, 4, 6, and 12, and that's it, right? Because any other order would not be a factor of 12, and therefore cannot be a subgroup of that group of order 12. So potential subgroups, or say subsets of size 5, 7, 8, 9, 10, 11 cannot be subgroups. They can't be groups, right? Or subgroups of that group. So it's a very powerful result and gets used a lot in future theory. In a future session I will actually show you the texts that I will use for higher level finite group theory. I'll show you the text for M1, that's first year master's level, M2, that's second year master's level, and PhD 1 level, if you're interested, if you find this stuff beautiful and powerful. Okay, so before I launch into what a coset is, let me say a little bit about its significance. To prove the main result of this lecture, and like I said, one of the main results of the whole course, namely Lagrange's theorem, you need the concept of a coset, because you use that concept to prove Lagrange's theorem. So the concept of a coset is the powerful and vital means to prove Lagrange's theorem. Right? So what is a coset? Well, you start with any group G and find a subgroup of that G, so call it H. So H is just a subgroup of this G, whatever group, and take any member X of your subgroup H. So in a sense there are two kinds of cosets. There's a so-called left coset and a right coset, and the three bars here mean by definition. Remember, I tend to use that to denote by definition. So the left-hand side is defined by what's on the right-hand side. But don't be confused. Here again, I use the three bars. This is in a different context, and the meaning of this symbol has changed. In this context, it means this number is congruent to this number. Right? So be conscious of that. Same symbol with different meaning, different use, depending on the context. Right? So here's just by definition. So the definition of a left coset is you take that element and you binary. I could put a binary operator here. You binary operate on with that member, any member of your subset. Oh, sorry. That should be G. Okay. So you take any member of your group, and you binary operate with that member on your subset. Now this itself is shorthand. So again, I've got three bars by definition. So this X of H, what does that mean? Well, it's the result of what you get when you binary operate x, whatever member you choose, and if this is of order n, you'll have n of these products, if you like. So x, any member of your group, then binary operates on each member of your subset, your subgroup H, right? So just take x inside, so you'll get, x binary operation E, well, that's just x, and here you get xh1, xh2, and so on. These are the members, the full list, the members of this subgroup, right? So you get that. So this list here, this set, is by definition this x of h, and remember that's a shorthand. Now that is called, this here is the left coset. Why left? Because you've binary operated on H on its left. You've got this x here on the left side of H. Now similarly, the right coset is defined this way, but instead of it being xh, it's now hx. Okay, so the x is now on the right hand side. So the coset that you get is of this form. So it'll be just x h1 x h2 x dot dot dot. Okay. So that's all a coset is. It's just you take an arbitrary, any element of your group. You take a subgroup of your group, call that H, and then you just multiply H either on the left or the right by that element. Right. So XH, that's a left subgroup. HX is a right subgroup. Right. Now let's actually do an example now. Now, from the previous lecture, we were talking about dihedral groups. So if we take D3, so we're talking about the symmetry operations of an equilateral triangle, right, D3. And remember, well, here's a subgroup of G, just E, A, and A squared. Okay, that's a group, and it's a subgroup of G. All right. Well, let's form all possible cosets of this subgroup H. So each of these E, A squared, B, BA squared, they are all possible members of G. Right. You can have any element belonging to your group. And for D3, remember the size or the order of a dihedral group, Dn, is 2n. Remember that from the previous lecture? So n in this case is 3, so we'll have six members of D3. And here they are, E, A squared, B, BA squared. You're familiar with that from the previous lecture. All right? So we have 6 candidates for 6 ways we can form left cosets. And we could do a similar story by having putting the x here, in case E, A, whatever, on the right-hand side. So we have another 6, so in a sense 12. All right, well, let's just do it for left cosets. So EH becomes this, right? Here are your, like that would be E, and that would be H1, H2 here, right? So just left multiplied by E, so you get EE, EA squared. Well, it's just A squared. And a similar story when your x is A, so you get AE, A cubed, right? Now, remember from theory of dihedral groups, if this is n here, A to the n is E. Now, in this case, n is 3, so A cubed here would just be E, right? So you can rewrite this as this. And a similar story, so A squared E, A squared A squared, A squared. So this just becomes A squared, that's A cubed, that's just E, okay? And this is A to the 4th, which is A times A cubed, which is just A, right? And so on. So you do the algebra with A's and B's. We talked quite a bit about that in the previous lecture. Okay, now look, have a look at the results here. These are the 6 possible left cosets. Now 3 of them are the same, and the other 3 also the same. So in effect, you only have 2 different cosets. Now that's often the case. When you find the cosets of a subgroup, with respect to a given element, the cosets will often, there'll be repeats. Some of them will be the same as each other. So don't expect them to be all different. In fact, typically you'll get repeats, right? So in this case, this concrete case, we only had two different cosets. So that's one coset, and there's another one, different one, right? So only two different cosets. All right, let's do a concrete example now. Well, we've done one just there, but here's another one. Okay, so you're given a group. In this case, it's just the set of integers, right? And the binary operation is plus, just ordinary addition. And your subgroup is 3z. What does that mean? It's just shorthand for the set, infinite set, of 0, plus or minus 3, plus or minus 6, plus or minus 9, dot, dot, dot. Okay, so that's what this means, right? Okay, so let's find the left cosets. So we'll do like xh rather than hx, which is the right coset. So let's do xh, so here, okay. And we have to do it for all members of G, right? All members of G. Now, G is an infinite set, so